Hello and welcome back. In section 2.5 we're going to go over some graphing techniques. Specifically transformations. So the first couple you'll already remember from your Math 100 days or the equivalent that you took somewhere else. Only now we're doing them with a couple of functions that we didn't get to play with in Math 100. So we'll start with just a basic f of x is x cubed. So remember, when we say basic with respect to graphing functions, we don't mean as in we're considering this stuff easy. We're saying it as in only one thing is happening right now to our inputs. Just for ease of reading what I'm doing, I'll keep using those fun little stamps. So 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. That's a little bit far off course. So then -1 quantity cubed, -1, -2 quantity cubed, -8. So we have our function that we remember from section 2.4. G of x, we're going to take this previous graph of x cubed and we'll add, let's say, 2 to it. We're looking just kind of one input at a time. 0 cubed is still 0. 0 plus 2 is now 2. 1 cubed is still 1. 1 and 2 is worth 3. 2 cubed is still 8. 8 and 2 is worth 10. -1 quantity cubed is -1. -1 plus 2 is +1. And -2 quantity cubed, -8. -8 plus 2, -6. So notice that each point in red has a point in blue exactly 2 units above it. So it's as if I picked up the red graph and slid every single point up 2. And we would see a similar thing. I guess I'll do this last one in black. H of x, we'll do an x cubed. Well, let's do just a -1. 0 cubed is 0. 0 minus 1 is -1. 1 cubed is 1. 1 minus 1 is 0. 2 cubed is 8. 8 minus 1 is 7. So unsurprisingly, as you hopefully remember from your Math 100 or equivalent somewhere else days, anytime we have a situation where we have y is f of x plus some constant, we'll just use k for some constant. K is in a set of reals. Y is the graph of f. Shifted one of two ways: up if k is positive, down if k is negative, and each time absolute value of k units in either up or down depending on the sign on k. So next we'll take a look at what happens if we have some addition or subtraction but happening inside of some grouping symbols. So this one we'll do the cube root next. How about that? So we'll start with our basic. F of x is the cube root of x. So that's one that you didn't get to play with much in Math 100. So square root and cube root, we have to be a little bit more careful picking out our inputs. We want to pick either perfect squares for square root or perfect cubes for cube root. Well, 0 is a perfect cube. Cube root of 0 is 0. Cube root of 1 is 1. Our next cube root, you should hopefully kind of be thinking in terms of the previous example with x to the third. 2 to the third is worth 8, which also means that the cube root of 8 is worth 2. Cube root of -1 is asking what can you multiply 3 copies of to reach -1, and sure enough, -1 is your solution to that. And cube root of -8 is -2. So we have the same basic shape, only along the x-axis instead of along the y-axis. So the next one we'll look at, we'll do g of x is equal to the cube root of, well, let's say x minus 4. So this is, by the way, also expressible as g of x is f of the quantity x minus 4. So what I like to do when I have some action happening inside of grouping symbols, so remember radicals count as grouping symbols even though they don't write the parentheses for us, they do count as one of our sets of grouping symbols. I like to think what I would have to do for an input to get back to 0. So if I plug in a 4 here, I get a 0 underneath. 4 minus 4 is 0, cube root of 0 is 0. So I had to plug in an x value of positive 4 to get a y value of 0. To get a y value, an input of 1, since 1 is another nice, pretty perfect cube, I would have to plug a 5 in there. 5 minus 4 is 1, cube root of 1 is 1. Next perfect cube didn't happen until 8, and I'd have to go all the way to 12 to get that. So that's a little bit past where our graph goes. That'd be somewhere right around up there. We also have -1 as a perfect cube root. If I plug in a 3, 3 minus 4 is -1, cube root of -1 is -1. So 3 for my input gave me -1 for an output. Next perfect cube going left after that was -8. I'd plug in an input of -4 to get a -8 down there. So -1, 2, 3, 4, and the cube root of -8 is -2. So this one, you might notice that instead of shifting up or down, we shifted, in this case, to the right. That might seem a little surprising. The minus moved us in the positive direction. Inside the parentheses, it kind of works backwards from what you would initially kind of expect. But if you think back to that idea of how do I get a 0 in here, you'll move in the right direction. Do that one. That's a busy enough graph. We'll do another one. Bad angle on that one. That's okay. Let's see. So this one, and we'll do our friend the square root. So square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2, and square root of 9 is 3. After that, I would have to go all the way to 16 for my next point. So this one I can only fit 4 lattice points on there as is. Well, now let's say g of x is square root of, we'll move the other direction, so we'll say x plus, I don't know, 5. Again, think of that idea, how do I get a 0 inside? To get a 0 inside, x would have to be a -5. We'll do these guys in red. So a -5 input would give me a 0 output. To get a 1 underneath there, sure enough, plug in a -4. -4 plus 5 is 1, square root of 1 is 1. To get a 4 underneath, -1 would be my input. To get a 9 underneath, +4 is my input. To get a 16 underneath, next perfect square after that, I still need to go to 11, which is just slightly past where I can go on this graph. So notice the minus moved us to the right, the plus moved us to the left. Inside works backwards. So then we can say in general, y equals f of x plus, we'll just say c for constant. It's the graph of f shifted right, absolute value c units. To the right, that was when we had a minus, so c had to be less than 0, or left, absolute value c units. C is greater than 0. If z equals 0, we're not moving left or right. So we don't have to bother covering that one other case. So those hopefully you're familiar with. So I'm going to kind of walk you through the procedure that I want you to follow when you're asked to graph these things. And most of our graphing is going to be done without calculators. There will be a part where calculators are permitted and a part where calculators are not permitted. This will be on the no calculator part. So you're going to have to know how to do these using the transformations. So graph by transformations. You're going to have to label each stage. So f of x is, let's do just a quadratic. So let's say x minus 5 squared minus 2. So you always start with the basic function. Every one of your graphs is going to start with that. So y equals x squared. I'll do that in black. And occasionally I've seen people just drawing the just rough basic shape and showing like literally 1 point or no points in a basic curve. I want you to use the techniques that you're seeing in the videos. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, and that's as far as we'll typically go. 4 squared, we would go to 16. That's a little farther than this 10 in each direction grid goes. -1 quantity squared flips us to +1. -2 quantity squared flips us to +4. -3 quantity squared flips us to +9. So there's our y1 graph. And remember, you do need these labels. They are worth points. You do need the first stage as well. So any shifting left or right, we can do that in one step. So f of x is equal to x minus 5 quantity squared minus 2. If we have any stretching, we'll have to do that separately. So minus 5 on the inside tells us we're going to be moving every point that's in black to the right 5. Minus 2 outside, everyone in black is dropping down 2. So every one of these points, I'm going to count to the right 5. and down 2. The right 5 and down 2. Right 5 again, and down 1, 2. Right 1, 2, 3, 4, 5 again, down 1, 2. Right 5 down 2, right 5 down 1, 2. And right 5, those are 6 apart, so right here, and down 1, 2. So we just picked up that previous graph and moved it to the right and down. We didn't change the shape at all. The next thing that we take a look at, now we do start changing the shape a bit. So this next one, let's see, we haven't played with absolute value in a while, so we'll do an absolute value graph. So let's say we'll do these in, I guess, red to start, since that's what's in my hand. Absolute value of 0 is 0, absolute value of 1 is 1, absolute value of 2 is 2, absolute value of 3 is 3, and so on. Absolute value of negative 1 is positive 1, absolute value of negative 2 is positive 2, and so on in that direction. So we've done plenty with adding and subtracting. Now we're going to get to multiplying. Well, let's do 3 absolute value of x. And the first one of these, we'll kind of talk through calculating the points and then kind of get the idea of what's going on. So absolute value of 0 is still 0. Anything times 0 is still 0. So this one's still nailed down on the origin. Absolute value of 1 is 1, but 1 by 3 is 3. Absolute value of 2 is 2. 2 by 3 is 6. Absolute value of 3 is 3. 3 by 3 is 9. And after that, we're clearly going to be off the grid going that way. Moving the other way, absolute value of negative 1 is positive 1. 3 times positive 1 is positive 3. Absolute value of negative 2 is 2. 3 by 2 is 6. And you hopefully should expect to see negative 3 paired up with positive 9. So this time the graph didn't move left or right at all. What happened was, in this case, a vertical stretch. All of our old outputs got multiplied by 3. And that is generally what will happen with multiplication when we have anything outside of whatever grouping symbol, absolute value, parentheses for the square, square root, cube root, etc. In general, y equals a times f of x. We'll multiply each y value of f by a, and that's their new location. That does also include if we multiply by negatives. So let's say we have, if they ask us to graph f of x is, we'll do negative 2 square root of x plus 3 minus 1. We'll combine all of the stuff that we've done so far. And again, we're going to be graphing these by hand, and we're going to be using transformations to get us there. So our first stage is going to be boiled down to its most basic. This is a square root function. That's the key feature of it. So square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. Square root of negative kicks us off of the real numbers, and these are two real number lines. Let's see, we'll reserve the red for later. So, order of operations, I have things happening in grouping symbols, I have multiplication, I have subtraction. Grouping symbols come first. So square root of x plus 3. And remember, inside works backwards, so we're going left 3 units on each of these guys. So the shape didn't change at all. We just picked up the black graph and moved it to the left 3 units. So that took care of our grouping symbols. So next, we'll take care of the multiplication. So all of the y values of the previous stage, of the blue stage, are going to get multiplied by -2. 0 times -2 is still 0, though. 1 times -2 is -2. This has a y value of +2. 2 by -2 is -4. This has a y value of +3. 3 by -2 is -6. So two things happened with that. We had a vertical stretch because we multiplied by something bigger than 1. And we also reflected across the x-axis because of the negative, the change in sign. And then our last stage is going to be the full thing. That's just dropping everyone in that last stage down 1 unit. So that's what I'm looking for, is showing your stages. I want to take a look at one more of these. We'll do an f of x is equal to, let's do 1/3 of x squared. So no frills, no shifting to worry about. But this time we're multiplying by something between 0 and 1. Exclusive on both, of course. So our basic function on this, the key feature, is the square. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. You hopefully did enough of those in your Math 100 to be able to do those basically in your sleep at this point. So remember, when we're multiplying by something outside, we're just then taking our old y values and multiplying them by that outside quantity. 0 times anything is still 0, but 1 times 1/3 is 1/3. 4 times 1/3, 4/3 is 1 1/3. Nine times 1/3 is 3. We would even be able to fit the next one. 16 times 1/3 would be 5 1/3. After that, 25 thirds, we can even fit that. That is 8 1/3. "36 thirds" is 12, though. That's off of it. So this one was vertically compressed. We smashed it down by multiplying by something on the open interval 0, 1. So bigger than 1 in absolute value, it will stretch it vertically. Between 0 and 1, it will compress it vertically. So then the next one, we're going to take a look at being given a function in picture form, but not told exactly what it means. And they have us then working on what the graph will look like based on some inputs in the function notation. So this one I'm going to do just with a ruler. And let's see, the horizontal ones I'm just going to kind of eyeball in by cutting them in half each time. That's going to be close enough. And let's see. All right, so again, I'm not going to tell you what the function is. We're just going to call this function y equals f of x. Vertical scale, each of these is just going to be worth a 1. So here is some function and we're going to graph y equals f of 2x. Again, you might notice that the action is happening inside. If it's happening inside, one, it's going to work kind of backwards from what we sort of might expect. And two, we want to think, okay, let me plug in a couple. To get to 0, I would still just plug in a 0. So what happened at 0 before is staying at 0. This guy isn't moving. The next key piece here happened at pi over 4. Or I'm sorry, at pi over 2. So if I plug in, let's say, an x value of pi, what happens at pi in blue happened at 2 pi in red. Except I went too high there. So then to figure out what happened at, say, 3 pi over 2, if I plug in 3 pi over 4 and double it, I'm at 3 pi over 2. So what happened at 3 pi over 2 is happening at 3 pi over 4. what happened at pi, now I only have to go as far as pi over 2. 2 times pi over 2 gets me back to an input of pi. What happened at pi over 2, now I can plug in a pi over 4. So notice what happened this time is the shape was pushed in, this time horizontally. So we multiplied by something and we compressed it instead of stretching it. Again, inside works sort of backwards from what you would think. So we only have to go half the distance to get the same job done because of this times 2. All right. Let's see, so we talked deflections, stretching, compressing. We'll do one more of these. This one again we'll do freehand, and then we'll just do the homework from there. And again, for these couple that I'm not giving you a function on, I'm not doing a lot of work with the scale. If I give you the actual function, I would put more detail, obviously, into it. And this guy's heading this way. All right. So in this one, let's see what I want to do. We'll go through here. Here, down here, up here, up here. And this one we'll make them kind of sharper ones. We'll keep it as a function though. I still want to pass the vertical line test. So let's say this is y equals f of x. And we'll do blue. I want to do f of opposite of x. Well, 0 is its own opposite, so this guy that happened with an input of 0, he's staying with an input of 0. But what happened at 1 is now going to have to happen at -1. That way, opposite of -1 returns me to what happened at the positive 1. So what was over here, now it's over there. What happened at positive 2, now it's happening back at -2. What happened at 3, now it's happening at -3. What happened at 4, now it's happening at -4.